Okay, I'll just ignore that. So it's sideways right now. So what we have here is the Robert Frost poem. We've all seen this before. And what's the first line? It's a simile. And we're going to, what is simile? It's a way to show equivalence, which is a math term, equivalence between two things. Two things are similar, equivalence, right? And so we can take a simile, like she is as in a field, a silken tent, take that simile. Uh, this has to be true. What is true about the silken tent better be true about the sheep. If both of these, in other words, the physical attributes of the silken tent must resemble the spiritual attributes of this person. If they resemble and there is certain equivalence, then this line can be written. Okay, but what happens is it's a simile, but the rest of the poem is there to prove the simile is true. Okay, so as you read down, where does he start? What does he start with? Does he start talking about the woman or the silken tent? He starts giving us physical attributes, features of the physical tent right there. So we get that what is a silken tent? What kind of features does a silken tent have when it is on the ground in a field? We find that at midday when a sunny breeze, when a sunny summer breeze has dried the dew and all its ropes, the tent's ropes relent, so that in guise it gently sways at ease, and its supporting central cedar, that is its pinnacle to heavenward. Right now, what are we getting? All and only attributes of the tent, physical attributes. How it's set up with the pole, it's got ropes, that is right. And then we get this line right in the middle and signifies the sureness of the soul. When we get to this line, sureness of the soul, are we still talking about the tent? Kinda, but according to me, not really. This is the moment when we start talking about the soul of the sheep. So we started with the silken tent, descriptions of the silken tent, and somehow managed to get to the sheep right there. And then the rest of the poem, starting with the soul, is all about who this woman is. Even though the language and the lines and the imagery is still of the tent. Because there's no way we can say that this description is not about a person. All right, so when we see that, what we do is, so let's look at, are you buying this? I am buying this, okay. So let's see. It signifies the sureness of the soul, seems to owe not to any single God, but strictly held by none, is loosely bound by countless silken ties of love and thought. Again, when you see love and thought, tents do not think, and they're not in love. So we are talking about a woman who has ties with men, Robert Frost and other men, ties to her children, her two kids. By countless silken ties of love and thought to everything on earth that compass round, and only by one going slightly thought. And she holds her balance and poise in the world so effortlessly that only when one of those ropes are slightly taut, tighter than other, when there's a pull from somebody else, the kids want her to spend her time with them rather than with Robert Frost. When that is just accidental or something like that, in the capriciousness of the summer air is the slightest bondage made away. Okay, so this is a woman who can handle ties of love really very well, just like how our tent is pitched on the ground. Okay, so what do we do with a simile like she is as in a field, a silken tent? We can take that first line and think of that first line as an implication. Right. Cool and not cool yet. I'm going to use, oh, fuck. This is going to take forever. This is really tiny. I need to go down here. Oh, here we go. Oh, okay. It's going to be very big, guys. All right. So what I did is this morning, I'm like, okay, if this is a simile, and then what happens here is that it's easier. This is a key point in math proofs. It's easier to move from the silken tent to the she rather than from the she to the silken tent. In other words, the truth about the she, about the spiritual attributes, the attributes of ties of love that the she has, it's harder to go from by starting with she and proving that she has all those attributes that leads us to the silken tent. So we want the silken tent to be the antecedent right here. So you go, if a silken tent in a field, we assume that everything, all the physical features of the a silken tent are true. We will start the proof there. And once we expand on what it means to be a silken tent in a field, this should hopefully lead us to the sheet. So we start here, and this is the idea of a direct proof in mathematics. You start with the antecedent, and you deduce is the word, from the antecedent, the conclusion that she is super cool. Okay. So lines 2 to 6 of this poem, from here all the way to so from let's actually 2 to 6. These are the lines in which the poet is expanding on the idea of what a silken tent in a field looks like, what its features are. Once he has expanded completely, he's confident he's now confident that he has finally this description of the tent resembles the she, and he has proved it. So in this case, the proof kind of, if this is the antecedent, this is all of the conclusion that he needed to prove. Okay. All right. So this will be clear in a bit. All right. So what is a theorem for this class or for the first proofs class? It's usually just a implication. Okay. So a theorem is a statement that says that if this is true, that implies that this thing over here is also true. So the theorem says if this is true, then that thing is also true. Okay. And so, in other words, a theorem is a statement of fact that says that two things are related to each other. And the theorems in a first course in mathematics are usually in the form of this thing called implication. Implication means that we're going to have a if and then structure. And what I'm going to do is I'll actually, let's start with, I could throw in, we just saw that, right? I threw in the silken tent here and the she here. I could also bring two mathematical ideas. So I'm going to say that, for instance, n squared is odd. And both this thing and this thing is supposed to be true. Otherwise, it doesn't work. So the first the antecedent here, that's the term here. The antecedent is n squared is odd. And if that is true, then that implies that n is also odd. All right, and then what happens is this better be true and this better be true, then this whole implication is going to be true. So the only way this implication is going to be true, and what's the other name for the implication? Theorems. All of our theorems in this class will be one-line statements like that, with an if and an then. And we will always have some kind of statement, mathematical statement here, that we will say that if we assume that to be true, we need to show that this is true or not. So is this statement a valid statement right now? Yes, because this better always, the antecedent always better be true. This is always assumed to be true. And right now I have T here. Okay. What if I put this? Is this true now? It is not valid anymore because we always need two T's. One true here and true here. Write that out here. True, false. Then the whole implication is false. Okay, all right. So that is what an example of a implication that we will be calling a theorem. So this is a theorem in mathematics, a discovery in mathematics that tells us that if you have some n squared, it will be odd. And if it is odd, then, so you have some n, we don't know if it's odd or even, but if you square some n, some number n, it's going, and if it is odd, then that number itself better be odd, otherwise it won't. So in other words, if you square an even number, you're going to get not, you won't get an odd, you'll get an even number. So if this was 2, you will get 4. 4 is an even number. This has to be an odd number, and that comes out here. This can only be true if n is always odd. Okay, so if we assume this to be true, then we need to show that n is actually odd. It is not, it is not evident. I mean, it is evident to us, but in mathematics, the rigor comes in proving even something that silly. Okay, so now let's keep going here. And we are going to write here. We assume this to be true. So I'll put a true here. Okay, and then this better be. So this is assume. What do I have here? 1 second, I need to cheat quickly. Make sure we're getting this right. Yeah, we assume this, and we over here we reduce. So if we call this P and this underlying statement as Q, okay, so we're going to call this P just to simplify it and increase the generalization, right? Remember, we're always moving between the concrete and the abstract levels or levels of generalization. And again, raise your hand as soon as you get lost, okay? Or frightened or start panicking, you need to raise your hand. So we assume P to be true, as in n squared is odd, and we deduce because, and we are supposed to deduce, if you're doing a direct proof, we deduce from P the truth of Q. Okay, is that? I need. All right. So does that remind you of what happened before? We assumed that the silken tent was true, all its attributes were true, and then we deduced from the silken tent, first 6 lines, uh, everything we could, and that led us, so we were able to deduce from the silken tent the truth about the sheep. Yes? Okay, next, let's move on. So we're going to call, so usually in your textbooks, you're going to get this kind of a mathematical statement. And this is just an instance of this form. So this is the Platonic form, right? Maybe it exists somewhere. And this is an instantiation of that with that. Okay, so this we're going to call an original. This is our original, let's say, basic form. So we're looking at forms here. So basic form. Let's do this. Oh. And we're probably running out of time, aren't we? Theorem, implication. So for us, a theorem is just an implication. So when we get this, what we do is we can just do a direct proof, right? We assume this to be true, expand on this, bring everything we know about mathematics into our expansion, deduction of P, and we finally end up at Q. And it turns out that if we assume P, we will get Q, which means Q is true. So, so let me repeat that again. We assume P to be true. We deduce Q from P, therefore Q is also true. And we are done. And so then the whole statement has 2 T's, two T here and a T here. And this is the, what happens is sometimes it's not that easy to expand the P and get to the Q. So then what you do is you reformulate this and you do, just to make sure, the contrapositive. So again, we start here. I'm going to put assume.
Wait,
Yes.
so
Good.
is this like, if they say something about the tent, if that, then it's true about her?
Yes. If we assume everything about the tent is true, once we assume that and we work with the tent, expand the all the ideas with the tent, that should, if it leads us to the she, then she is also true. That all her qualities will also be true because we were able to take all the qualities of the tent and were able to get to the she. And therefore, all her qualities are true as well. The sureness of the soul is there because the tent is so perfect. Okay. All right. We assume here, and then I'm going to put here. We start here, right? So that we assume this to be true. We start here in order to get to this guy here. I'm doing to get, let's call it get here. Okay, next. Next we have, so what happens is sometimes it's easier to go from here to here. So for instance, it's easier to go from this statement of mathematics to this one. But what if it was the other way around? What if it's almost impossible to assume P to be true to get to Q. So then what we do is we do the contrapositive. We love this guy and we bring it here. Okay. So what we do then is we say, if Q, then P. Are these two implications equivalent? No, right? You've got the P here and Q here. You got Q here and P here. How do we make these two implications identical? And this is where you bring in your NOT, not. And you put another knot here. Now these two guys are equal. Okay, and how did that happen? God came in. What we're assuming is that um, uh, why are they equal? I know this, but I can't explain it. So let's move on. Should we just go on trust here, or should we? Anybody?
We can go on trust.
Yeah, trust. Yeah, okay. I trust in the dollar. This is this. What we do is we assume that so Q and P are both false. And if they're both false, we can move them around. Because if false, then false is, oh, yeah, that it can't record that. So I'm going to do it down here. If false, then false, and we haven't looked at truth tables. If this statement is, this whole thing is true. If bullshit, if this is bullshit, and then so is this. If this form, if false, then false is true. Okay. If we just had false here and true here, it would be false as well. Okay. It would be false. So if I had false here and true, this would be false. Because I have two false in a row, this is true. This is from the truth table of the implication. So we have that, but what we need, remember, we always need a T here and a T here. That's what we always want to prove. We want to prove in the end that both the antecedent and the consequent, the hypothesis and the conclusion are both true. If we have to show that, and then we've shown that the implication itself is true. So right now, what we've done is we switch them around and we've assumed that Q is false and P is false. So now we have if false, then false, it's true. And then all we have to do is put not here and then not here. What does that do? Not false, not false. If not false, what's not false? True. So now we have, now we can assume the antecedent to be true. And then this, the truth and what we deduce and expand, this true statement will get us this true statement. Because now it is true. So here, what we have done is we're saying that Q and P are both false. Okay, so okay, so we just put a not in front of this guy right there. Oh no, actually, what's the opposite? What's the negation is the word here of n is odd? Excellent. See, math major right there. And then this would be n is even, and the square root of an even number is not odd or something like that. Actually, I will do that. I'm not a math major. That's why I'm stumbling on that. But you guys get that, right? Okay. So that is the logic behind it. What we always want to prove is an implication in which the antecedent and the consequent or hypotheses and the conclusion are both true. When we start the proofs, we can only assume this side. When we get to that, if we can get to that, then that is also true. Yes.
What do you do? How do you, so like say that the first one's true and the second one's false. How would you know? Because you're trying to.
So then what happens is, if the first thing is true, we assume it to be true. We never get there. If
So what would you?
so, we say that the theorem, the original theorem was incorrect. Very good question. Very good question. So, in other words, if we assume the antecedent to be true, and we can't deduce, expand, bring other things in to get here, we fail in proving the implication. And we say the original implication was incorrect. And therefore, please remove this from your textbooks. Literally, they will remove it. If you make a theorem or statement about some mathematical truth, and you write a proof, and then somebody checks the proof and turns out it's wrong, the theorem gets cancelled. Okay, all right. Okay, so now everybody gets this? Yes, this is now clear. We need the not and the not to make it true. And then what's happened? Why did we do this? Because it's easier to go from Q to P. And the only way we can bring Q here and P over here, and this thing is still identical to this, is we have to bring in the not, as I showed you. What we do is we use this form. If false, then false, and put a not. Yes. No. Very good. Thank you. Yes.
To go from the.
So what happens is, a very good question again. What you get, the homework assignment is you get if P, then Q, and the professor says prove it. You try the direct proof. You try to go from P to Q and you fail. You're like, this thing is too much. I can't handle it. What if only this Q was here? I could easily do that. But the only way to bring the Q here is to put the not in front of it. And to take P over there. So we're switching the antecedent and the consequent. And we're only allowed to do that when we stick in the not for the reasons as highlighted here. All right, we good? Okay, so there's a third formulation. So usually what happens is we will see a direct proof. Most of the time, what we do is we don't even do this one most of the time. Most of the time, we do proof by contradiction. So let's look at that one now. Okay. Hopefully this thing is getting recorded. Lost 6 pounds since this semester started, which means math is good. I'm actually teaching 5 days a week. I have to bike in, and I've stopped eating. I'm not going to exercise. I'll just stop eating. Okay, now we have something called proof by contradiction. So you are given. Oh, the proof. And then it looks like the proofs we'll do on Friday. We'll start at least do 1.5 proofs, go into Monday, do all 3 proofs rigorously. As in, no, like very slowly, proof by contradiction. And then you can go home and tell your parents, I was an English major, but we did math and it was beautiful. And I didn't panic and there was no homework. I don't say that. Okay, so it turns out the professor gives you if P, then true, then Q, and you can't, contrapositive doesn't work, or you usually go, I know how to do this. Proof by contradiction is always the easiest way to go. Okay, so again, in this case, where do we start? We start here in order to get here, or get there is what we're calling it. Okay, so now, what do? We go if. So we're not looking at this, we're looking at this guy here, right? So we are going to reformulate the implication so that we can do a proof by contradiction. And how do we do that? We keep the P here. We don't mess with the P. We still get to assume it true, okay? And then what do we do? This is all we do. We do, what is this? This is saying if you assume P to be true, and if you can reduce from P, Q, then Q will be true. What we do right now is we say that not Q is actually true. So we take the opposite of the conclusion. So in other words, if this was our theorem, we would say that n squared, n whatever n is, if n squared is odd, then n is even. which is patently false because we already established that the theorem is true. So we say something false here. I'm going to write that down. We are saying, remember, in the other two, we only assume the truth of the antecedent, and then if we got to the consequent, we said, yes, the consequent is true as well. Over here, what we're saying is, we are assuming that the not Q is true. We're assuming that our new consequent with a not in front of it is true. So we say that the conclusion, this new conclusion is true. Okay, and then we just do a direct proof on it. In other words, we start here. Oh no, sorry. Apologies. In this case, we always start here. We start here. If you start here, where do you have to go? But this is what we need to show, right? In our new formulation, this is where we're supposed to go. We already start there by assuming. So we're really fucking up. So that is a good point. You would think in your head, aren't we supposed to go there? No. We start here and we expand and we want to stay there. This is still assumed to be true. All antecedents in all the formulations are always assumed to be true. So what happens is we expand, we deduce, we're trying to get somewhere. At a certain point, our consequent starts to look like our antecedent, and that's when we bring it in. And so we bring the antecedent in. So we don't, we start here and let's just say stay here. But at a certain point, we bring this in. So this is to be, we bring this in. So this is what we do. Bring in at a certain point in the proof. And when we bring that in, what happens? We see a contradiction. As soon as we see the contradiction, we go, this idea of negating the consequent and assuming it to be true was wrong. Therefore, the original theorem, as it was stated, was actually true. And so we have proved. Because what did the professor give you? The professor gave you this. You said, I want to do a proof by contradiction. And I'm going to say that the conclusion is actually opposite of what the theorem states by putting the not there. I'm going to assume that the negation is actually true. I'm going to still stick with the fact that the antecedent is true. And let's see if I can move from here to over there.